Okay, hello everyone. Today we are studying a new unit. Finally, we are learning about the equilibrium. So, what extent will a reaction proceed? Let's begin. So, today is the first day we learn about what is equilibrium. So, based on your understanding of the English literacy, so equilibrium is probably means something that's being balanced, right? The same. And yeah, so two opposing process, they are having the same speed and thus they are being balanced. No apparent change is happening. If you are having an open system, so the rate of evaporation is higher than the rate of condensation, and you will see some of the water that are being lost. Whereas if you are having a closed system, because the water molecules, they are being trapped under this lip, they cannot escape outside of the bottle. Therefore, the rate of the evaporation is equal to the rate of condensation. Therefore, the water that's inside the volume doesn't really change that much. The things we need to remember from thermochemistry. So, system is the portion of the universe that's being considered. Closed system is that no matter is possible to escape. Isolated system is a system that nothing can escape, even the energy. And the equilibrium can be approached by both sides. And if the final equilibrium state is there's some liquid and there's some gas over there, and if you begin with the liquid, some of the liquid will turn to gas and go to this form. Also, it could be happening begin with the gases and it condense into some of the liquid. And we are assuming that it is the same temperature and also the same pressure under those conditions, and the characteristic of a dynamic physical equilibrium. So observable property do not change with time. Constant microscopic property. The system is closed and the temperature and pressure are constant. Opposing internal process proceed at the same rate. Okay. And yeah, and we will be considered the system below and decide whether it could reach the equilibrium. So in the end, this water will be getting saturated by the salt, and some of them are dissolved into ions, and some of them are still there because it's being saturated. It cannot be dissolved anymore. And how does the diagram looks like? Because we have a negative dipole and this is the positive dipole, and it is attracting the negative of the chlorine, and this is attracting the positive sodium, and that's how should the diagram looks like. And if this thing here, a small amount of sodium chloride is added to lots of water, this is just a solution, and therefore there's no equilibrium. Ice cubes are placed in water at 0 degree, so nothing is getting escaped. So the ice stay ice and the water is still water. There's no ice formed or no new water being formed. Therefore, it is a equilibrium. And the water is heated to boiling to a beaker, so the water is just escaping, right? They are not going to condensing back, so in the end you will get just no water left. So no. Consider the following equilibrium equation. So what does the equilibrium equation tells us? So molecules formed and molecules are breaking up at the same time. Each A atoms goes just with one B atoms, and molecules must consist of one of each. What doesn't the equilibrium equation tells us? The number of A atoms present compared to the number of B atoms, the number of molecules compared to the number of atoms. So this is just like stoichiometry. We don't know that how much actually the amount is. We just know that with respect to one another, what is the ratio of one compared to another. If you recall the grade 11 stoichiometry, you should be very familiar with this. And let's do one example over here. So we are given, this is losing 1 m of the hydrogen, and at the end there should be no hydrogen left according to the stoichiometry. So this ratio should be 1:1:2. So 1:1:2, and the reactant side they are losing. So the other side should be forming. So this is negative, this is positive, and we just apply the change to the original amount. We get the final equilibrium state of each substance. And yeah, equilibrium can be happening at the both sides actually. Suppose you are having a lot of H2I2, okay, 2HI, and the equilibrium is going to balancing something out. Therefore, this thing is declining, this one is rising. Also, if you're having a oh yes, my bad. This is H2 plus I2, okay? If you are having extra H2 and I2, you're gonna decrease that amount and try to balance it and increase the hydrogen iodine. Yeah, this should be acid, so sorry. And yeah, it can also be happening at the other side where you have a lot of hydroiodine acid, and you decrease that and balancing H2 and I2. And this is just some stoichiometry, and you just given one number and you need to figure out the rest. So suppose now we are given the final amount, we can know the change, and using that change we and the stoichiometry ratio, and we just apply that, and just be careful with the negative sign. One side is reducing, then the other side must be increasing, and we apply the change and we get a final amount. And these kind of problems are called the ice equation. And predicting the effect of various change of the equilibrium, the chatelier principle. Consider this reaction. So one side must be endothermic and exothermic, and another is exothermic. If heated is added to the whole system, well, equilibrium is always going to try to balancing out the resources it have. So it will try to take some of the heat and absorb that to balancing the equation. If you are taking away some of the heat, it will try to release the heat to balance it. Yes. Making sense? So if you have like extra this thing here, it will go to the other side to balancing out. Okay, so endothermic will be favored, and if this thing is removed, the heat that's being is restored will return to this side to balance it. And we'll talk a little bit about the pressure and the volume. So if you are increasing the pressure, that means the overall volume is going to be decreasing according to the ideal gas law, which is the pressure P over here, and the volume equals to the number of moles of the substance, and this is R is going to be the gas constant. You don't need to care about that, and T is the temperature. So here we know that the volume is decreasing, so the equilibrium is trying to balance it and having less moles of substance. For example, if the volume suddenly decreases, so we have 2 moles of substance on the reactant side, no, the product side, and we go to the other side, we'll have 1 mole of reactants. So the total amount of the molecules are decreasing because they are combining. So it will be favoring the reversing reaction. And similarly, this one, originally the reactant sides have 4 different substances, and you reverse, and you're gonna go to the other side to have 2 moles of substance. To the right, this one, the reactant and the product, they both have the same amount of molecules, so no shift will be happening. And an inert one does not react with any species. So for a rigid container, the volume of the container is actually not changing. Even if the some of the other gases are present and they may be adding some extra pressure, but the volume of this container is fixed, so we don't care about this. Whereas if the problem is specified to be a non-rigid container, as for example a balloon, we know that if there's more gases add to the balloon, it's going to increase the volume. Then we need to take into account of this extra gas that we increased into this container, and that's the whole idea of this. And we will have the molecules shift to the other side, and we should also talk about the catalyst. So just imagine this, that originally 2 reactions, they are having some kind of speed, right? And the one is going their speed is kind of having a ratio. The equilibrium state adding a catalyst will not be changing, but the speed of that equilibrium state will be forming, will be faster, because the catalyst is increasing the speed of both the forward and backwards reaction by a certain ratio, so the overall net change is becoming faster. And yeah, that's where we're getting stopped, and thank you for watching this video, and see you in the next one.